record. Let's see, where is it? There it is. Okay, we're recording again. Okay, so let's actually do this. Okay, let's get started. All right, so here's how this works. What if I told you the derivative of a function was f of x equals f x squared plus 4, okay? So when we integrate this function, we call its antiderivative capital F of x, okay? And so the idea is whatever function that is, it's very important that the derivative of capital F prime of x is equal to f of x. You guys memorize this, please. You know, I should actually have that formula in the WUBI. It is such an important formula. We define capital F of x such that its derivative equals the original function they gave us. So we have to undo this process, and you guys have gotten pretty good at this. You know that it has to have an exponent of 3, but that has to, we have to put a 3, we have to divide this by 3 so that those undo each other. And then we have 4x here. Okay, and then we could add an arbitrary constant c to this because we want to anchor it. Okay, the value of c will determine the anchor. Okay, and just to check that, you guys, if you take the derivative of that, check this. If you do f prime of x, you take this, you'd bring the 3 out front. You'd have 3 times x squared over 3 plus 4, and then the derivative of the constant is 0. So I'm going to say plus 0. And you'll notice, sure enough, that would give us x squared. That would give us x squared plus 4, which is indeed equal to f of x. So I did it correctly. Okay. All right. So this goes in the WUBI. And put this in there too, you guys. Add that into the WUBI. Okay. Put that in there. All right. Once you've identified the function capital F of x, whose derivative is f of x, I wrote the function. I should probably call this a function. Once you've identified a function, capital F of x, whose derivative is f of x, we simply evaluate the definite integral. And we say definite because it has expressions for the upper and lower bounds. Sometimes you have an integral where they don't give you those upper and lower bounds. And so that's called the indefinite integral. But this one's called the definite integral. And basically it equals this, okay? To be more precise, it technically would be this, f of b plus a constant minus f of a plus a constant, okay? Technically, that's what it equals. But this is fine to say this because if you expand this out, you end up with f of b, capital F of b plus c minus capital F of a minus c, and those c's cancel. So you end up with f of b minus capital F of a, capital F of b minus capital F of a. So that's where that comes from. Okay, so let's see what we do here. Okay, so suppose we want this area on the under this curve from 0 to 5. Remember, we did that here and we got 75, which is way too big. Okay, let's try this out. Here's what we do. We write this down. We take the integral from 0 to 5, the lower bound, the upper bound. We put f of x in here, x squared plus 4. With respect to x, this is the height of each rectangle. This is the width of each rectangle, okay? And that equals, we have to undo differentiation here. So this would be x cubed over 3 plus 4x plus c. And now we're going to evaluate this. And this is the notation we use from 0 to 5, okay? That's the notation that's used to say we're going to evaluate that, okay? Sometimes they don't put this bracket here, and sometimes they just do a line here. And I just like to include what it is I'm evaluating here. So the way this works is we put a 5 in here first. So we have 5 cubed over 3 plus 4 times 5 plus c. And then we subtract this, just like it says here. Then we subtract, let's put a 0 in here. We'd have 0 cubed over 3 plus 4 times 0 plus c, like so. And what I'm telling you is, folks, what is amazing is this is the exact area under that curve, which I just think that's really exciting. We're going to get the exact area under this curve. We're in this few seconds of work here, we are literally adding up the areas of an infinite number of rectangles. And I just think that's cool. This is the process for doing it. You're adding up an infinite number of rectangles that are infinitely thin, and you're going to get a finite number. It'll be less than 75. We know that. So here we have 125 thirds plus 20 plus c minus, this is all z minus c. Okay, and my c's go out, and I have this. So I'm going to rewrite that. You guys, I know you guys love to grab a calculator, and on the BC Calc test, you can grab a calculator and round to 3 decimal places. Problem is you're going to go on and do other things beyond the BC Calc test. So I want you not to forget how to add fractions, okay? So let's do this. Let's write these with a common denominator, 125 thirds plus 60 thirds, which is 185 thirds, okay? So that is going to be, I hope, less than 75. And there it is. We have 61 2/3, okay? So that's the exact area underneath our curve, and I just love that. I think that's the coolest thing ever. Okay, that's the exact area. You can have 500 rectangles, you can have 1,000 rectangles. You're just gonna get closer and closer and closer to that answer. But there's the exact answer. Okay. All right, number 4. Write the integral and calculate the area under the curve of the cosine of x from 0 to pi over 3. So the integral would be the integral from 0 to pi over 3 of the cosine of x times the width of each rectangle. Okay, so notice this is the if I pick a value of x here, this is the height of that rectangle, okay, that tiny little rectangle, and this is the width, the x. And so I'm adding up an area of every single rectangle between 0 and, oh, look at this. This is pi over 3. Oh, this says 1 here. So pi over 3 would be like 3.14 over 3. So just a little more than 1. Okay, that's what's going on there. So this edge here is not 1. This is pi over 3. Okay, so we're going to add them all up. Okay, so we just need to think of, well, what function is it that has a derivative of the cosine? Well, that would be the sine of x, and then plus c. And then you guys, you run into issues when you write this stuff down. Do we mean the sine of x and then plus c, or do we mean the sine of this quantity x plus c? So one way around that is to write it like so. That's one way to handle it. You could put the constant in front, although the calculus people who do calculus never do that. Okay, and then we're going to evaluate this thing. So here's how you'll often see it, from 0 to pi over 3. That's often how you'll see it. They'll just put a bar there, and that indicates evaluate it first at the upper bound and then subtract at the lower bound. So this would equal the sine of pi over 3 plus c, and then minus, and then we put in 0, the sine of 0 plus c, like so. Okay, and so the sine of pi over 3, well, that's on the unit circle. Pi over 3 is basically a 60-degree angle. The sine is the height on the unit circle. That's root 3 over 2 plus c. The sine of 0 is 0 minus c, and we get the square root of 3 over 2. And so that's the area of this piece right here. And is that at all reasonable? This is what, 0.866, 0.867? The square root of 3 divided by 2, 0.866. Does that seem reasonable? Well, the area of this is 1. And so the area of this funny shape here seems like less than 1 seems reasonable. This little bit of area wouldn't quite make up for all of that. So that seems pretty reasonable, 0.866. And sometimes people fuss about this symbol. If you make an equal sign with a little dot there, that means it's a decimal approximation. Okay, because really the square root of 3 over 2 is really not equal to 0.866. It's irrational. This has an infinite number of never-ending random decimal places. So anyway, that's a symbol that you could use. Okay, and then number 5, I mean, you can just go to town on these things. Here's a cubic. All right, we have a cubic function on the interval from 1 to 5. And so once again, we just figure out the area going from 1 to 5. This function x cubed minus 2x squared plus 7x plus 1 dx. Don't forget the width. So what we're saying is we're going to take every single value of x from x equals 1 all the way to 5, and every single value of x that we choose, we're going to draw in a little rectangle like this, like a Riemann sum, you know. And then what's the area of that one rectangle? Well, it's the height of this. It's the height of the rectangle, which is f of x, and then times the width of it dx. And that's exactly what we have here. That's f of x, and that's dx. Okay, so we just need to do an antiderivative of this function. This would be x to the 4th over 4 minus 2x cubed over 3 plus 7x squared over 2. You'll notice with these polynomial functions, I just divide by the new exponent. And then I could write 1x to the 1 and then divide it by 1, right? Plus x and then plus a constant. And I'm going to evaluate this going from 1 to 5, okay? And I don't know. I like to put this in here so it's clear what's being evaluated at 5 and what's being evaluated at 1. And so I simply plug this in here. Let's put a 5 in there. I'd have 5 to the 4th over 4 minus 2 times 5 cubed over 3 plus 7 times 5 squared over 2 plus 5 plus c minus, and then let's put a 1 in there. This would be, okay, 1 to the 4th. I feel silly writing that down. That would be 1 over 4 minus, put a 1 in here, would be minus 2/3. Put a 1 in here, that would be plus 7/2 plus 1 plus c, like so. Okay, and then I just need to clean this up. 5 to the 4th is 5 times 5, which is 25 times 5 times 5, 25 again. That's 625 fourths minus, this is 125 times 2, which is 250 thirds, plus, this is 25 times 7, 175 halves, plus 5, plus c, minus a quarter, plus 2/3, minus 7/2, minus 1, minus c. Okay. And gosh, I wish I had written that down underneath here, because then I could kind of combine my like terms like this, right? That would be 624 fourths. And then these guys go together. That would be minus, let's see, 250 thirds plus 2/3. What is that? Minus 248 thirds. And then let's see, these two. 175 minus 7 is what? 168 halves. And then 5 minus 1 is plus 4. And then the c's just go out. Plus c minus c, those just go out. Okay. And I'm feeling like everything's going to work out except for this guy. Okay. 8 plus 4 is 12, plus 2 more is 14. So 3 is not going to evenly divide into those, but these guys are going to work out fine. 624 divided by 4, we have 156 minus, let's see, 248 divided by 3, minus 82 2/3. Okay, and then plus 168 halves is 84 plus 4. So let's see. These two guys add up to 160 plus 84, like so. So 160 plus 84. All right. And then I'm going to subtract the 82, right? And I have 162. And then minus that 2/3 would be 161 1/3 square units. And there we have it, you guys. That is the exact area of that deal. Okay. So there we are. If it turns out I made a mistake on here, I will post a second video if I screwed up in my algebra. It's very common to make a mistake here, and I'm only human. If I did make a mistake, I'll post a second video. I'll make a note for you that I messed some up. Okay. All right, you guys. Take care, and I will. I'll see you soon. Okay. All right, you guys. Bye bye. Take care.